as for summarization for this chapter, again I explain these notes. Okay, this is the degradation or restoration model, and again during our the first part of the lecture we talk about the first cases. Okay, the first cases where there's no blurring effect, your image G only affected with additive noise, and then what you do is that okay, of course the model can simplify can be simplified as in the diagrams, and then of course you must assume your noise is a random signal. So since the noise is in random signal, so you cannot represent it in mathematical expression, except you can unless if you can I'm sorry, except you can just represent the random noise by using the probability distribution function. That is the only way we can represent the random signal or random number. See, so how to obtain the PDF or probability distribution function? So you capture a plain image by using your image modality or your hardware or image modality. So I just simplify the example just by using your digital camera, not okay, not just not we will not talk about other image modality. Just imagine that you want to investigate the degradation effect that happen to your camera, digital camera, for example. So what you want, how you want to solve it? You just take your digital camera, you capture the plane surface, like a walls and so on. But if you don't have accessible to that hardware, like for example, the digital camera is come from, it's a your friend's digital camera that you cannot access. So what you can do is that you can ask your friend to send some picture that capture by using that camera to you. So then, for example, this is the image that captured by that camera that have been sent by to you by your friends. Or what you can do is that you just crop the background which containing the plane surface like that. So that's another way to capture the plane surface. And then what after that, you from this plane surface, of course, our hypothesis states that if this plane surface is our ideal F here, if you plot the histogram, you should only see only one bar, because since all pixels or all color is similar, the value should be similar. So if you plot the histogram, it should belong to one color only. But because of your camera is affected with additive noise, this should not happen. Once you crop your image, which is this one, if you plot the histogram, and you will see the some histogram there, and then from that histogram you need to observe the shape. If this kind of shape, it should be harmonic noise. If it's a bell shape, it should be Gaussian noise. So that's how we know. And then let's say this is harmonic, should be the harmonic noise. I'm sorry, not harmonic, a uniform noise. So what you do, then you need to calculate all the parameter involved as in the uniform noise, the mean, the mean, the standard deviation, the A parameter and B parameter, and so on, based on after you convert this histogram into PDF. So that is what we do as before, and we already discussed that one. Second case, where actually you assume there's no additive noise. The only your image G is only affected with blurring function or blurring effects there, H. So for this one, okay, of course you can simplify your block as in the figure there. So that is the equation represent your G, and then you of course at this spatial domain is a convolution, at this frequency domain is a multiplication. And then now the objective is you need to model or estimate your H. Okay, in order to do that, there's a three-way: observation, experimentation, and mathematical modeling that we have discussed in during our second part of my lecture notes there. And then once you know your H, then you can apply the inverse filtering by just divide your G and your H, then you get your estimate F. And not just that, inverse filtering also can be used for the second or the third case, which is when your image is affected with both additive noise and uh, blurring function there affected or degraded your image. So you still can use the inverse filtering on condition that you need to cascade with the low pass filter, ideal low pass filter, in order to make sure that the additive noise is not dominant in the equation that we have discussed before. I hope you already get the overall picture about the restoration, image restoration, where it should be significantly different from the image enhancement, where everything need to have a justification. There's a mathematic model. If you want to know the noise should be model. Is it a Gaussian, is it a uniform noise, or is it a gamma noise? So you need to model, and it's very objective as compared to image enhancement. It's very subjective. Once you see your image is not good, then you just apply the averaging or sharpening, histogram equalization, and so on, without investigating and without any justification, without a strategic procedure on how to investigate one by one, step by step. You can see that the restoration is better than in this situation, where it's investigate step by step. First, you need to investigate what happened to your image, what actually the factor degraded your image, and then once you know what is the factor, you need to try to find out the mathematic model can express the noise or the blurring function before you select the best approach in restoration blocks there. So which is a little bit more advanced than image enhancement. I think that's all. Thank you.